SwayamPrabha. Digital India. Educated India.
Welcome back. Let us continue the discussion on the kinetics. So, we are looking at a global reaction and the multi-step mechanism, like the reaction which goes through multiple elementary reactions, and then from there once you look at the elementary reaction, there are multiple species or the radicals which are formed during this elementary process, and using those and the concept of equilibrium, we are trying to find out the rate constant. So, where we actually stopped in the our discussion is that finding this using the concept of equilibrium, and you correlate the equilibrium constant from the partial pressure, we can find out the molar concentration which can be related to mole fraction and partial pressure. So, this is my molar concentration which is can be related to that, which is nothing but Pi by RUT. So, here the molar concentration is actually connected with the partial pressure and the mole fraction. Now, we can define the equilibrium constant based on the molar concentration, like Kc related to Kp. So, we can find out Kp equals to Kc, which is RUT by P naught C plus D plus minus A minus B, which is 2.41 A, or one can find out Kp equals to Kc by P naught summation of this. So, that is your B. So, one can actually correlate the rate constant, and now we can find out or the Kc. So, the Kc is Cc dd divided by AA and BB, which is product of Xi divided by product of reactant, where Xi this. So, 2.42. So, that you get Kf by Krt equals to Kct. So, that will get you 2.43. For bimolecular reaction, Kc is nothing but Kp. So, this is what you get. Now, there are some approximation which is very common in this equilibrium analysis is the steady state approximation. So, the steady state approximation talks about, or this is the analysis of the any reactive system which can be simplified by applying the steady state approximation to the reactive species or the radicals, because as we have seen the intermediate reactant shape, we get all these radicals, and using this steady state approximation we can find out those details. Steady state also justified when the reaction forming the intermediate species is slow, while the reaction destroying the intermediate species is very fast. That means whatever is formed, it is getting consumed at a faster rate. So, this is quite a good ease of approximation. So, the result of that is that concentration of the radical is small in comparison with those of the reactants and products. So, what we can take again an example. For example, the NO formation mechanism, which is very well known, is the Zeldovich mechanism. So, we take that for NO formation, where you have O plus N2, the first step it forms NO plus N, N plus O2, K2, NO plus O. So, here this first reaction is slow and rate limiting, while the second one is quite fast. Now, if one has to look at the net production rate of N atoms, so this will be dN by dt equals to K1 O N2 minus K2 O N2. So, this is what you get. So, that means in the particular step, now if you allow the rapid transient to build up the N, so your dN by dt will approach to 0, which means this, if I correlate, this would be K O N2 minus K2 N O2. So, my N at steady state is K1 O N2 divided by K2 O2. So, this you can mark as 2.45 and this is 2.46. Now, the time rate of change of NSS is d NSS by dt is ddt of K1 O N2 K2 O2. So, that one can find out by taking the derivative of that thing. So, this is how one can, using the steady state approximation, and find out all these details. Now, we can move to the what happens when you have a unimolecular reaction. So, we will look at for unimolecular reaction. So, we first consider, or let us consider a 3-step mechanism. For example, A plus M, which is goes to A star plus M, then you take A star plus M, which goes A plus M, then finally K unimolecular to products. So, essentially these are your 2.48 A2 C. Now, in first step or step 1, what you do? So, the kinetic energy which is transferred to A from M, A has increased internal vibrational and rotational energies and becomes an energized A molecule to A star. So, because of this you get two possible scenarios for A star. So, there are two possible scenarios for A star. Okay. So, number 1, A star may collide with another molecule and goes back to A. which is actually happening at this step here, where A star is colliding with another molecule and goes back to A, or what may possibly happen, A star may decompose into products, which is essentially this step, where A star actually decomposed to a product. Now, one can find out the rate at which the products are formed. So, this would be products equals to K unimolecular reaction to A star. Now, the net production of A star is d A star by dt, which is K E A m minus K d E A star m minus K unim. So, this is where you get your net production rate for A star. Now, you apply the steady state approximation for A star, which will be d A star by dt equals to 0. From there, we get the concentration for A star is K E A m K d E plus K unimolecular. So, this is what you get. Now, we substitute equation 2.51 into 2.49. So, what we get, d products by dt equals to K A m by K d by K unimolecular m plus 1. So, that is what you get for the products rate. Now, one can write in a different form for the overall rate of production of the product, where your A is going to products, that is through this reaction. So, one may write like dA by dt equals to products by dt equals to K F into A. So, this is alternative way of writing the production of products. So, K APP is nothing but the apparent unimolecular rate coefficient. Now, we equate two equations 2.52 and 2.54, which will yield that K FF equals to K E m K d E by K unimolecular m plus 1, which is 2.55. Now, 2.5 let us to explain this previous equation 2.55, which has explained pressure dependence of unimolecular reaction. Now, if your pressure is high enough pressures, okay, that means K d E m by K uni greater than 1, because m increases as the pressure is increased. So, what will happen? Kff when P tends to infinity, that K unimolecular Ke by Kde, which is your equation number 2.56. Now, this is the situation where you have high enough pressure. Now, if your pressure is low, so for low enough pressure, so there are two different conditions. So, what again we can say that K, this is very much less than 1. So, that means P tends to 0, which is Ke m. So, for two different conditions or the two different pressure dependency, that thing you can find out what would be the thing. Now, we have another important things when you look at the elementary reactions are the chain branching reaction. So, chain branching reaction. So, chain reactions actually produce one or more radical or the species that subsequently react to produce any other radical. So, that means in the reactions, so some more feature of chain reaction we consider a hypothetical, let us say chain reaction, let us say A2 plus B2 which becomes 2AB. Now, this is an hypothetical global reaction. Now, when you look at the chain reaction of this, there would be multiple steps of the chain reaction. So, there would be first step which is called chain initiation. That means A2 plus M which will form A plus M. So, that is your first step. Now, we will get once the initiation takes place, there would be chain propagating reaction. So, chain propagating reaction will involve free radicals like A and B. So, that means it will go A plus B2 to K2, AB plus B. So, that is your C2, B plus A2 which will go to AB plus which is C3. So, one you first get the chain initiation, after initiation there is a propagating reaction which will actually form the radicals. So, essentially A, B, these radicals are formed. So, now you go to chain termination reaction. So, chain termination reaction means the whole chain which got initiated, that will be now terminated. So, for this particular reaction, now you got M which will be K4 AB plus M. So, where AB is more like an stable product. Now, in the termination state you get a stable product like that. So, the concentration of A and B are quite small throughout the course of reaction. So, is AB at initial stages, thus one can ignore the reverse reactions and we can find out the reaction rate for the stable pieces like A2 which is K1 A2 M minus K3 A2B. For dB2 by dt equals to K2 B2A and then finally you get the product species dAB by d2 K2 AB2 K3 BA2 plus K4 A B M. Now, what we do? We use the steady state approximation for free radical A and B. So, you find out the dA by dt is 2k1 A2 m minus k2 A B2 plus k3 B A2 minus k4 A B m, which is for steady state that goes to 0. Similarly, for dB by dt equals to k2 A B2 minus k3 B A2 k4 A B m, which is 0. So, if you get the simultaneous solution of 2.61 and 2.62, that means this above two equations, we can find out for concentration of A. So, essentially solution of 6.1 and 2.62. So, that will get us the concentration of A, which will be K1 by K2, 2K2 M A2 divided by B2 plus K3 by K4 A2 by M into 1 plus K1 K4 by 2 K2 K3 M square by minus 1. So, this is a bit involved algebra. So, this is how the simultaneous solution of these two equations you get A. Similarly, one can find out for concentration of B. Now, with the steady state values of A and B, so now you get the steady state values of A and B, and we can find out dA2 by dt, dB2 by dt and dAB by dt for some initial values of A2 and B2. So, that is how for different reactions and using the steady state approximation for chain reaction, one can find out the other thing. Now, if we consider the simplest of the three, that means if you consider dB2 by dt, which is nothing but K1 by 2 and A2 m minus K2 K3 by K4, where A2 B2 by m into 1 plus K1 K4 2 K2 K3 by B2. So, the last two equations can be further simplified, and one may write K1 K4 m square by 2 K1 2 K2 K3 B2 is less than 1. So, if you do that, then since K2 and K3 is larger than K1 and K4 for steady state approximation to apply. So, this is valid for steady state approximation to apply. Then from equation 2.63 and 2.64, one can approximate that A is K1 by 2 K2 m A2 by B2 plus K1 square K4 8 K2 square K3 M3 A2 B2 square. So, dB2 by dt would be K1 by 2 A2 K1 square K4 4 K2 K3 M3 A2 by B2. So, in both the equations 2.65 and 66, the first term, which is this term and this term, they actually dominates at low pressure situation. So, when we have a low pressure situation, these terms are actually dominating. Now, concentration of A, one can look at that, depends on the primarily on the ratio of K1 and K2, and rate at which B2 disappears is also governed by K1. Now, increasing K2 and K3 increases radial concentration, but it does not have any effect on production rate of the products, and concentration of A and B are quite directly proportional to pressure, and reaction rate for major species scales with pressure. So, now provided the second term in these two equations, that means this term and this term, they are small. So, but at high pressure those two terms become quite important, because they will increase with the pressure than the first term do. So, K4 has some influence at high pressure, but not at the low pressure. So, when you look at these two expressions and try to find out the importance, so K4 has at high pressure it has importance, but at low pressure not, and chain branching reactions involve the formation of two radical species form a reaction that consumes one radical. For example, like this O H2O2 OH and OH. Okay. So, now once you do this, that means when you find out the steady state approximation using these chain branching reactions, find out this concentration expression, there are dependency of the pressure, and that will allow to see how that behaves, and then we will find out the chemical time scale calculation, or we will look at the chemical time scale calculation in the next lecture. We will stop here today. Thank you.